Take a microscopic protein crystal suspended in a cryoloop. Bombard it with intense ionizing energy, and the atomic lattice will scatter that beam into a precise geometric array of spots. The computer-based in silico modeling of structure determination gets most of the attention in modern biology, but that entire digital process is strictly constrained by the physical reality of data collection. This is the modern diffractometer. It is a highly tuned physical pipeline built to solve one specific problem: extracting a noise-free diffraction pattern without vaporizing the biological sample in the process. To achieve this, the instrument executes 4 necessary steps. It must generate the beam, focus that beam, orient the sample, and capture the resulting radiation. Treating this instrument as a tunable chain of quantum and optical interventions rather than a black box is the only way to avoid the trap of garbage in, garbage out data collection. This schematic shows the origin point of the pipeline, the X-ray source. Here, high-energy electrons are accelerated and violently decelerated as they impact a target material. Looking at the emission spectrum, this sweeping curve represents Bremsstra's law, a continuous energy background. Emerging from it are sharp, intense spikes. These are K-alpha lines, created when an electron knocks out a core shell electron, forcing a higher shell electron to drop down and fill the hole. The thermodynamic cost of this generation is severe. Over 99.8% of the electron bombardment energy is converted directly into heat. To prevent the target from melting, laboratory systems rely on water-cooled anodes spinning at 10,000 revolutions per minute. Even the most powerful laboratory rotating anodes share a strict bottleneck. Their maximum efficiency relies on those characteristic radiation spikes, meaning the resulting X-ray wavelength is permanently fixed by the specific metal used in the anode, severely limiting experimental design. Advanced analytical techniques, like multi-wavelength anomalous diffraction phasing, strictly require a tunable X-ray wavelength to extract subtle atomic signals. This is the layout of a modern synchrotron facility. It scales the X-ray source up to the size of a large building to achieve absolute tunability and extreme brilliance. In this storage ring schematic, electron bunches are accelerated to relativistic speeds. RF generators supply energy to maintain the orbit. Passing through bending magnets, they endure alternating magnetic fields, causing them to emit a tightly focused tangential cone of polychromatic X-rays down the beam tubes. The crucial metric of success here is brilliance. This equation measures the concentration of photons per second, passing through a single square millimeter, per milliradian of divergence. Scaling up to a relativistic particle accelerator is the only physical method to produce a beam brilliant enough, and with a precisely selectable wavelength, to analyze microcrystals and execute complex anomalous phasing. Whether generated in a laboratory tube or a massive synchrotron, raw X-ray emission is highly divergent and packed with unwanted wavelengths that will ruin a diffraction pattern. This schematic illustrates the solution. The green crystal monochromator uses Bragg diffraction to isolate the exact energy band, refracting it away from background noise. That filtered beam enters the narrow collimator tube, restricting the X-rays into a tight, nearly parallel bundle before reaching the sample. X-ray optics are the ultimate signal purifier. They discard the vast majority of photons, guaranteeing that only a brilliant, perfectly parallel probe hits the crystal. Looking closely at the central goniostat, we find the eucentric point. This is the precise microscopic intersection where the omega, phi, and kappa axes meet the incoming X-ray beam. The biological crystal must be systematically rotated through this precise intersection to capture reflection data across the entire solid angle. However, the intense ionizing nature of the beam rapidly generates free radicals within the crystal. At room temperature, these radicals would quickly diffuse and destroy the fragile biological lattice. To counteract this, a cryocooler nozzle is positioned immediately over the crystal, continuously bathing the sample in a stream of near-liquid nitrogen gas. Cryogenic cooling is a mandatory thermodynamic intervention. Freezing the radical diffusion allows the lattice to survive long enough to yield a complete high-resolution dataset. The final step of the pipeline is capturing hundreds of thousands of distinct reflections over a wide solid angle. This schematic of a 3x3 detector array details the conversion process. X-ray photons strike a fluorescent phosphor screen on the front, converting them into visible light. That light funnels down through these bulbous optical glass fiber tapers directly into the semiconductor array processing the signals. This multi-stage process creates vulnerabilities. Cosmic muons, or trace radioactive decay within the taper glass itself, can strike the silicon chip directly, creating false, impossibly sharp spots known as zingers. Newer pixel array detectors bypass this issue entirely. By skipping the phosphor step, they absorb X-rays directly into a silicon diode layer for instantaneous, shutterless readout. The area detector serves as the crucial final translator, converting the analog scatter of an atomic lattice into the digital pixel array that the processing software requires. We have followed the photon's journey from its violent generation and precise optical filtering through the cryogenically frozen lattice to its digital capture on a semiconductor chip. The diffractometer is an integrated physical chain of quantum mechanical exploitation, thermodynamic management, and precision optics. Understanding these hardware parameters allows a researcher to determine exactly what their specific protein requires, whether that is the extreme brilliance of a massive synchrotron beamline or a focused home laboratory source. Mastering the physical hardware of data collection is the absolute prerequisite for generating an accurate, high-resolution atomic model in the digital realm.